In this video, we will learn about 4+2 and 2+2 cycloadditions and how the outcome of these reactions can be predicted using molecular orbitals theory. This video has for objectives to make yourself familiar with the cycloaddition reactions, teach you the basis of a theory chemists use to understand this important class of reactions, namely the frontier molecular orbital theory, and introduce yourself to the Woodward-Hoffmann rules. So, what is a cycloaddition? A cycloaddition, as the name suggests, is a concerted reaction between two unsaturated molecules which combine to form a cyclic adduct. During the process, two pi bonds are broken and two sigma bonds are formed. Here are a few examples of cycloadditions. You probably are already familiar with the Diels-Alder reaction, but there is a wide variety of different cycloadditions. Feel free to pause this video to have a better look at these examples. First of all, let's do a bit of nomenclature. The symbolism with the square brackets identifies the numbers m and n of electrons in each of the molecules involved in the reaction. For example, in a Diels-Alder reaction, the diene brings 4 pi electrons and the dienophile brings 2 pi electrons. Hence, the Diels-Alder reaction is a 4+2 cycloaddition. The symbol A or S, A for interfacial, S for suprafacial, is often added as a subscript after the number to designate the stereochemistry of addition to each fragment. We'll learn about the signification of these descriptors in class. A subscript specifying the symmetry of the orbitals involved may be added before the number. Back to our list of cycloadditions, we can now characterize each of them with the number of electrons involved in the reaction. You may have noticed that some of the cycloadditions are further characterized as photocycloadditions. Indeed, some cycloadditions need to be activated by UV light to proceed. These are called photochemical cycloadditions. Other cycloadditions need higher temperatures to proceed. These are called thermal cycloadditions. At this point, you probably wonder why some cycloadditions are thermal and others photochemical, and how to predict their mode of activation. In the second half of this video, we will study the theory behind cycloadditions in order to explain and predict their mode of activation. To learn the theory, we will focus on two major cycloadditions, the 4+2 Diels-Alder reaction and the photochemical 2+2 cycloaddition. One of the theoretical frameworks that best describes cycloadditions is frontier molecular orbital theory, or FMO, developed by Kenichi Fukui from 1952. So, what is frontier molecular orbital theory? As you know, the electronic structure of a molecule is described by its molecular orbitals, represented on an energy diagram such as this one. The occupied molecular orbitals are populated with pairs of electrons, while the unoccupied molecular orbitals are represented empty. Fukui realized that a good approximation for reactivity could be found by looking only at the frontier orbitals, the HOMO and the LUMO of the reacting species. He understood that the HOMO of one molecule and the LUMO of the other molecule interact with each other according to the smallest energy gap. Examination of the overlap of frontier molecular orbitals of reactants affords an approach to the interpretation of reaction behavior. Qualitatively, two orbitals overlap well when they have the same symmetry. On the left example, you can see that the orbital of the diene and the orbital of the dienophile are in phase, because they are both symmetric relative to the plane represented by a dashed line. On the right side, however, the orbital of the top ethylene is symmetric, while the orbital of the bottom ethylene is antisymmetric, corresponding to zero overlap. In other words, if the mixing orbitals have the same symmetry, they overlap well and the reaction is allowed. In the opposite case, the reaction is called forbidden. To sum up, a cycloaddition will be allowed if the overlap between the HOMO of one reactant and the LUMO of the other is large, and the reactions for which the HOMO-LUMO energy gap is small will be favored. Let's have a look at the Diels-Alder reaction and use the frontier molecular orbital theory to study this cycloaddition. The first step is to look at the molecular orbital of ethene on the left side and of 1,3-butadiene on the right side. Next, we identify the frontier molecular orbitals, which overlap with the smallest energy gap. These are the HOMO of ethene and the LUMO of 1,3-butadiene. Then we look at the overlap of these orbitals. The overlap is qualitatively important, therefore the reaction is allowed. Now, let's have a look at the 2+2 cycloaddition. Similarly, the first step is to look at the molecular orbital of ethene, the same on each side this time, since we are looking at the reaction of two molecules of ethene. Again, we identify the frontier molecular orbitals, the HOMO of one ethene molecule and the LUMO of the other ethene molecule. And we look at the overlap of these orbitals. The symmetries of the frontier molecular orbitals are different. Therefore, the overlap is zero, so the thermal 2+2 cycloaddition is forbidden. Now, let's have a look at the photochemical 2+2 cycloaddition. Upon irradiation by UV light, some ethene molecule will be promoted to their first excited state. Here, we are looking at the 2+2 cycloaddition between one ethene molecule in the ground state, which molecular orbitals are represented on the left, and an ethene molecule in the first excited state, which molecular orbitals are represented on the right. The frontier molecular orbitals that gives the smallest energy gap are the HOMO of the excited state ethene and the LUMO of the ground state ethene. Note that the energy gap is much smaller than in the two previous cases. The frontier orbitals have the same symmetry. Therefore, the overlap is important. And this is why the 2+2 cycloaddition is photochemically allowed. Please note that the small energy gap between the reactants HOMO and LUMO correlates well with the low reaction temperature, as shown in the example at the beginning of this video. The second theoretical framework that best describes the outcome of cycloadditions is called the Woodward-Hoffmann rules. Robert Woodward and Roald Hoffmann devised these rules in 1965 by systematically examining the molecular orbitals of the reactants and products of pericyclic reactions. From their observations, they drew a number of rules that explain not only the reactivity of all pericyclic reactions, including cycloadditions, but also predict the regioselectivity and the diastereoselectivity of the products, as well as, to some extent, the activation energy of these reactions. The first rule states that all concerted reactions occur with conservation of the orbital symmetry over the course of the reaction. The second rule, specific to cycloadditions, predicts if a thermal or photochemical cycloaddition is allowed or forbidden, depending on the number of electrons involved and the relative positions and symmetries of the reactants. More explanations will be given in class, and the detailed method to use the Woodward-Hoffmann rules will be taught in class as well, using a series of examples. After watching this video, you should be more familiar with the cycloaddition reactions, as well as with using frontier molecular orbital theory to tell if a cycloaddition is allowed or forbidden. You also have been introduced to the Woodward-Hoffmann rules. This new knowledge will serve as a theoretical basis for explaining in class the regioselectivity and diastereoselectivity of cycloadditions, as well as predicting the relative reactivity of related cycloadditions. During the in-class workshop, we will also learn how to use the Woodward-Hoffmann rules for retrosynthesis and synthesis planning. In order to prepare for the class workshop activities, please write down at least 2 questions you have about the video you just watched. I hope you enjoyed this video. See you in class!